Welcome back, folks. We're going to continue on our journey with Kirchhoff's voltage law, KVL, and we're going to look at an example of a circuit that's a little bigger, and I'm going to write a number of KVL equations around this circuit using all sorts of different loops. There's multiple loops in this circuit, and we're going to follow a handful of them, and then at the end, I left one voltage that's not labeled, and I'm going to have you, I guess I'm going to do it, but together in this video, as if you're with me, miss you all, by the way, we're going to find that missing voltage. Okay, so I already drew the schematic, and it looks like this. And now we just have to pick some loops, and I haven't really thought out loops that I want to use yet, although I did cut or copy this so that I can make multiple copies of it as we work our way through it. Okay, so let's start off with this loop here. Okay, and I want to get a different color. So like I said in the last video, my habit is to start in the lower left. There's no reason I have to, because we're adding up a bunch of terms, and adding is commutative, so you can rearrange them. As long as they're all in there, they have the right sign, then you're in good shape. Okay, so I'm going to follow this loop along the orange path that I just drew. And as I follow that path, I see that I have 1, 2, 3, 4 elements that I'm going to cross over, so my KVL equation is going to have 4 terms, and they're all going to be voltages. I've given you the voltages for this circuit by the end of the semester, but really in a few weeks. If I give you this circuit with resistances and some other values, you're going to be able to go find all of these voltages yourself. And you do that by writing KVL equations. So that's why we're starting here. We're building up to working the other way. What if I have part values? How do I find the voltages myself? You can do it. I believe in you. Okay, so I'm going to start here, and the first component I'm going to cross is this 8.2 volt resistor. It doesn't have a name other than the voltage that's there, and I'm going from the negative side to the positive side, so the term is going to be positive. Okay, and then I write whatever's labeled here, and what's labeled there is a positive 8.2. Okay, and that's in volts. From that node, I move to the right, and I'm moving again from the negative side to the positive side, so the next term again is going to be positive, and it's going to be positive 8.5 volts. Okay, whatever's labeled there. If I had a negative voltage there, maybe I'll do that in a future video. If I had a negative voltage there, I would have written plus, and then I would have pulled that negative into the value. But that's not the case here. Okay, here we have, I'm at this node. I'm moving from this node over to here to the right, and I'm moving from the positive side to the negative side. So that's going to be a voltage drop, and it's going to be a voltage drop of 4.7 volts. Okay, now I'm at this node. I need to move down across this voltage supply. This is one of those multi-cell batteries I mentioned when I was introducing schematic symbols. We treat it as an independent voltage supply, and the long bar tells us where the positive side is. So long bar is positive, short bar is negative. So I'm going to move from the positive side, and as I move down, I'm moving to the negative side. So that's another drop. Okay, and that's in volts. Now I'm back to the node where I started. Okay, I have a big node down here along the bottom, and I'm back to where I started. So Kirchhoff's voltage law tells me that that has to be equal to 0. And a quick calculator check, if you haven't done it in your head by now, you can see 8.2 plus 8.5 minus 4.7 minus 12 is in fact 0. Okay, so it looks like we're in good shape in that respect. Okay, so that's one of the loops we can follow. Now, this is a law. You have to follow it, right? So any loop that we choose to follow in this circuit has to obey this law. So let's get another copy of our circuit down here, and let's pick a different loop. Let's pick the loop. Here we go. Let's start here and let's work our way around the outside of the circuit, and we'll come over here. Okay, I'm going to take the same approach, and now I see 1, 2, 3 components along that loop, and I'm going to have 3 terms. So I'm going to start here, and I'm going up across the 8.2, and it looks like that's going to be a voltage rise. 8.2 volts. And now I'm at this node. I'm moving to the right, and it's negative to positive, and I lost my unit there. Look at that. Must have copied it before I wrote those. And so I'm moving from left to right, so I'm going from negative to positive, so it's going to be a voltage rise, and it's plus 3.8 volts. Okay, I'm over here. I'm moving from the top to the bottom of the 12 volt again, and that's going to be from positive to negative, so it's a voltage drop, and that should all be equal to 0. Okay, so I could wave my hands and say, look, it all works out, but go check yourself. Okay, it's a good habit to get into, and it is in fact 0, so we're in good shape with that KVL. Now, I have habits, and habits make me get to the right answer as consistently as possible. Not always, but I try, and so should you. So my habit is to start in the lower left and go clockwise, but there's absolutely nothing saying that I have to do it that way. So I could take this same mesh, and I'll do this one in red, and I'll start up here, and I'm going to work my way around here. So I'm crossing the same 3 components, but I'm crossing them in the opposite direction. So if I start here and I move, this time I move right to left across the 3.8, I'm going to get a drop, okay, from plus to minus, so it's a drop, 3.8 volts. Okay, as I come down here, I move from top to bottom across the 8.2 volts, and that's plus to minus, so that's going to be a drop, and it has a magnitude of 8.2 volts. And now we're over here, and I'm going from bottom to top across the 12 volt battery, so that's going to be a rise of 12 volts, and that should be equal to 0. And if we do a quick check, look, all the signs are different, right? As long as all of the signs are different, that's okay, because I could take this whole equation and, should I do it? Should I do it? I can take that whole equation, and I can just multiply both sides by -1, and if I multiply left and right by -1, we're not changing it, right? And that's -1 times 0, that's rather boring. Okay, and I can distribute that, and I get positive 3.8 volts plus 8.2 volts minus 12 volts equals still 0. And other than these 2 terms being switched, now my signs line up. So pick a direction, move in that direction, be consistent with how you treat your signs as you move across your components, and you're going to end up with an equivalent KVL. So as long as you're consistent, you're going to be okay. All right, let's do a couple. Oh, see, now I don't have my circuit. I didn't think ahead. Okay, let's grab this one, because that's what I got, and we'll do a little nip and tuck on it to make the picture pretty. Okay, there we go. So let's get rid of that one, just so we're not distracted by that beautiful color of orange. Okay, that's the closest I can get. Well, let's just do that and that. Look at that, not too bad. Okay, let's think up, where else could I go? I can go up in here. I would usually ask you clockwise or counterclockwise if we're in the classroom, just to kind of emphasize that the direction doesn't matter as long as you start moving in the same direction. I'll start in the middle over here now, and I'll go clockwise, and I'm going to go right to left across the 8.5. So positive to negative is negative 8.5 volts. All right, now we continue following around here. We go from left to right. We're going negative to positive, so it's positive 3.8 volts. Okay, continue moving around here, and we go from negative to positive, so it's positive across the 4.7 volts, and that's should be equal to 0. Let's give it a check. Negative 8.5. Oops. Ooh, I can type in here. Check that out. Let's clear that. Negative 8.5. I'll sort out shortcut keys later. Plus 3.8 volts. Plus 4.7. And with any luck, we end up back at 0. So we're in good shape there. Okay, now you'll notice the one component that I haven't labeled. Oh, I should have copied it again. The one component I haven't labeled the voltage for is the current supply. And a lot of people starting out assume that there is no voltage across it, and that's simply not true. For current to flow, there needs to be some voltage to push the charge through the device. So it has a voltage across it. We don't often think about it, and we can go find that voltage by writing a KVL that includes the current supply in the loop. Okay, so I got to play this game again. So all right, so let me erase that. Okay, we're gonna have to pick a loop that includes that current supply. The other thing we're gonna have to pick is we don't know which direction the voltage is rising, so we have to kind of pick one and go with it. So this would be another case where I'd probably ask you in class, you want positive on top or you want positive on bottom, and you know, we can, you know, maybe we should work it both ways. Let's work it both ways. Okay, so let's go plus or minus there. And I don't know what that voltage is. I'm just going to call it V sub IS, the voltage across the current source. And I'm going to write a, I usually try to write the shortest loop that I can. Let's just go around this one. Okay, and I have 3 components in that loop. This one also happens to be a mesh. I have 3 components in that mesh, and I'm going to have 3 terms in my equation, and that's going to look like this. So we're going to start down here. We're going to go up 8.2 volts. Okay, from here to here, we're going to go up 8.5 volts, and then using this polarity that I picked, and I picked it out of the blue, I won't lie, I'm going plus to minus, so it's going to be minus VIS, and then I'm back to where I started. Right, I started in the lower left here, and that's going to be equal to 0. Okay, so now I have one equation and one unknown, so I can now go find that voltage, and in its simplest form, this is what we're going to use KVL for, is finding unknowns in our equations. So solving for VIS, I just got to add it to both sides, right? So let me write it this way, kind of flip the sides of the equation. It's going to look like this, and it looks like VIS is going to be 16.7 volts. Okay, so I can come back over here and I can label that 16.7 volts. Now, if I did that correctly and I followed all the rules and my initial analysis of this to set up the voltages, if it's a legitimate set of voltages around here, they should all agree. No matter what loop you take, they should all agree. And we should see that we get 16.7 volts no matter which path we take. So let's take a different path, and let's get fun with it, because we can take any closed path through the circuit and KVL should apply. So I'm going to take this path. Okay, so I'm going around this lower left mesh, and I'm going around this top mesh, and coming back, and as long as I start and stop at the same place, we should end up with a consistent result. Okay, so let me buy a little real estate down here. I'm going to go up across 8.2. I'm going to go up across 3.8 volts. Come down here, hang a right, and we're going to go up across 4.7 volts, and then we're going to drop, I'll use the value, 16.7 volts, and that should be equal to 0. So if we did our math right on the last one, it should match our value there as well. And oh, my calculator is going to be over this, isn't it? Let's see if I can move it without causing... Oh, no, it's behind me. Don't maximize. Thank you. Let's see. 8.2 plus 3.8 plus 4.7 minus 16.7, and that's equal to 0. So KVL held again in that case. So we can use it to hold unknown. We can use it to solve for unknowns. If there's an unknown voltage, maybe that unknown voltage is across a current supply. The current supply is going to have a voltage across it, and it should be consistent no matter which path we take around the circuit. Okay, so a lot of what we do in analysis is going to be writing these equations, and we might work with them symbolically. I'll sort that out later. But we got to get comfortable with which direction we're moving across the voltage rise or drop, and how the sign corresponds with that. So hopefully these help you out. I'm going to have you write some in some web work problems, which everybody gets excited about. So go ahead and get at those, and stay tuned, and good luck.